Hello students, welcome to the lecture on Bayesian Estimators 2. Let us recall, unlike MLE, Bayesian estimators assume the parameters theta to be a random variable with the prior PDF f theta or prior PMF p theta. The estimator uses the posterior PDF f of theta given x or posterior PMF p of theta given x using the Bayes rule. We associate a cost function or a loss function c of theta minus theta hat with the estimator theta hat. Cost function is a function of error. A Bayesian estimator solves the optimization problem. This is the optimization problem. Minimize c bar of theta hat over theta hat. C bar of theta hat is equal to integration from minus infinity to infinity, minus infinity to infinity, c of theta minus theta hat into f of x theta dx d theta. This is the average cost function we want to minimize. The MMSE estimator, minimum mean square error estimator, minimizes the mean square error and is given by this expression theta hat MMSE is equal to integration from minus infinity to infinity theta f of theta given x d theta. That is the conditional expectation of the random variable theta given x. So, MMSE is given by the conditional expectation of theta given x. In this lecture, I will focus on another Bayesian estimator known as the maximum a posteriori probability map estimator. I will also introduce another estimator known as the minimum absolute error MAE estimator. Let us start with hit or miss cost functions. Hit or miss cost function, also known as uniform cost function, is given by this c of theta minus theta hat is equal to 1 if the absolute value of theta minus theta hat is greater than equal to delta by 2 is 0 otherwise. So, this is the plot of the hit or miss cost function. If error is within plus minus delta by 2, then cost is 0, otherwise cost is 1. In other words, if parameter theta lies between theta hat minus delta by 2 and theta hat plus delta by 2, then the cost is 0, else cost is 1, and here this delta is very small quantity. Now, corresponding to this hit or miss cost function, the Bayesian risk function is given by expected value of c theta minus theta hat, that is integration from minus infinity to infinity, minus infinity to infinity of c of theta minus theta hat into f of x theta dx d theta. And now, as earlier, we will take this fx dx outside. So, we will get the minimization problem as the minimization of this integral from minus infinity to infinity, integral from minus infinity to infinity c of theta minus theta hat into f of theta given x d theta into fx dx. So, we have one inner integral and one outer integral. Since fx is always greater than equal to 0, therefore, the double integral will be minimized whenever the inner integral is minimized. So, therefore, our minimization problem is to find the minimum of this integral from minus infinity to infinity c of theta minus theta hat into f of theta given x d theta with respect to theta hat. Now, using this cost function, we have the cost function value at this interval is 0. Therefore, we can write the minimization problem as minimize over theta hat integral from minus infinity to theta hat minus delta by 2 f of theta given x d theta plus integral from theta hat plus delta by 2 to infinity of f of theta given x d theta. Thus, the Bayesian estimation problem is now minimized over theta hat integral from minus infinity to theta hat minus delta by 2 f of theta given x d theta plus integral from theta hat plus delta by 2 to infinity f of theta given x d theta. Now, this integral is equivalent to this expression, because if we integral suppose this expression from minus infinity to infinity, we will get 1, because this is a density function. Therefore, this minimization problem can be expressed as the equivalent minimization problem of this integral 1 minus integral theta hat minus delta by 2 to theta hat plus delta by 2 f of theta given x d theta. So, now we have to minimize this part, since this is a difference. So, this minimum will be same as maximizing the integral. This integral, if we maximize, then this difference will be minimum. Therefore, we have to maximize the integral theta hat minus delta by 2 to theta hat plus delta by 2 f of theta given x d theta. And this we can approximate as f of theta given x at point theta equal to theta hat into delta for small delta, because our delta is very small. Therefore, this integral we can approximate by this expression. Now, consider this approximation. Delta is a constant. Therefore, this approximation will be large whenever this quantity is large, and as delta tends to 0, f of theta given x at theta is equal to theta hat is maximum when it is equal to the maximum of f of theta given x. We will illustrate with this diagram. Suppose this is my theta and this is my f of theta given x. Now, this density function has a maximum at this point. Now, if I put my theta hat here, theta hat, then this area, suppose this area, this interval is delta. So, this area will be maximum if I put theta hat at this point corresponding to this maximum. Therefore, the estimator is the value of theta for which f of theta given x is maximum, and is called the map estimator. Maximum is a posteriori probability estimator. We will denote this estimator by theta hat map, because this is corresponding to the maximum a posteriori PDF. So, this point is theta hat is equal to theta hat map. So, this point is equal to theta hat map. Thus, theta hat map is argument over theta of max f of theta given x. Now, f of theta given x, that is equal to f theta into f of x given theta divided by f x. Therefore, theta hat map will be argument theta of max f theta into f of x given theta divided by f x. Now, this f x does not involve any theta. Therefore, theta hat map is arg max theta of f theta into f of x given theta. Now, if f of theta given x is differentiable, the conditional PDF or a posteriori PDF is differentiable, then theta hat map will be given by del f del theta at theta hat map is equal to 0. So, partial derivative of the a posteriori PDF at theta hat map is equal to 0. Or in terms of the log likelihood function, we can write del L del theta at theta hat map is equal to 0. Either we can solve this equation or this equation. The above two equations are known as the map equations. Example, consider single observation x that depends on a random parameter theta. Suppose f theta is equal to lambda into e to the power minus lambda theta for theta greater than equal to 0 and lambda greater than 0. And the likelihood f x given theta is equal to theta into e to the power minus theta x, x greater than 0. Find the map estimator for theta. Here lambda is assumed to be known. We have the a posteriori PDF f theta given x, that is equal to f theta into f of x given theta divided by f x, and taking the logarithm log of f theta given x equal to log of f theta plus log of f x given theta minus log of f x. So therefore map estimator is given by, as told earlier, del theta of log of f theta plus del theta of log of f x given theta at theta hat map must be equal to 0. So now we have to take the partial derivative of the given, suppose PDF is given here, so we can find out log of f theta. Similarly, we can find out log of this expression, and if we take the partial derivative, we can write del theta of log lambda minus lambda theta plus del theta of log theta minus theta x at theta hat map is equal to 0. So we will take the partial derivative and then put theta is equal to theta hat map. We will get minus lambda plus 1 by theta hat map minus x is equal to 0. So from this we can find out theta hat map, and the estimator is given by 1 by lambda plus x. So this is the maximum a posteriori estimator. Now let us see the relation between ML and MAP estimators. From f of theta given x equal to f theta into f of x given theta divided by f x, we can write log of f theta given x is equal to log of f theta plus log of f x given theta minus log of f x. Now this partial derivative of this with respect to theta is 0. That will imply that log of f theta del theta log of f x given theta del theta at theta hat map must be equal to 0. So therefore we have this map equation del theta of log of f theta plus del theta of log of f x given theta at theta hat map must be equal to 0. And if we examine the ML equation, this is simply del theta of log likelihood function at theta hat MLE is equal to 0. So we see that this expression contains this term, but it has one additional term. There is additional contribution from the prior PDF. This is the contribution from the prior PDF. When f theta is sufficiently flat, in that case log of f theta will be also flat, so that this quantity del theta of log of f theta will be approximately equal to 0. So this will be approximately 0, so that theta hat map is approximately will be equal to theta hat MLE. So when f theta is sufficiently flat, that means its slope is very small. In that case log of f theta will be also flat, so that its slope will be also very small, nearly 0. In that case theta hat map will be equal to theta hat MLE. That means if the parameter has more uncertainty, in that case theta hat map will be closer to theta hat MLE. We will consider one example. Let x1, x2 up to xn be IID Gaussian with unit variance and unknown mean theta. Further, theta is known to be a zero mean Gaussian with variance sigma theta square. This is the prior PDF, that is Gaussian with variance sigma theta square. Find the map estimator for theta. We are given f theta. This is the PDF, prior PDF, 1 by root over 2 pi sigma theta square into e to the power minus theta square divided by 2 sigma theta square. So, this is the zero mean Gaussian with variance sigma theta square. And the likelihood function f of x given theta, that is also Gaussian with unknown mean theta. So, that way f of x given theta is equal to 1 by root over 2 pi to the power n into e to the power minus summation I going from 1 to n of xi minus theta whole square divided by 2. This is the likelihood function of random data. Now, we will consider the map equation del theta of log f theta plus del theta of log fx given theta at theta hat equal to theta hat map must be equal to 0, and this will give us this relationship theta by sigma theta square minus summation xi minus theta I going from 1 to n at point theta equal to theta hat map is equal to 0. So, this will give theta hat map is equal to 1 by n plus 1 by sigma theta square into summation xi I going from 1 to n. This is the expression for theta hat map. And now, we can manipulate this expression. If we divide by n, then multiplied by n, therefore, n divided by n plus 1 by sigma theta square into 1 by n into summation xi I going from 1 to n. Now, this quantity is theta hat mle. So, therefore, theta hat map will be equal to n divided by n plus 1 by sigma theta square into theta hat mle. It is a scale version of theta hat mle. Two observations are made. Number one, as sigma theta square goes to infinity, then this quantity will become 0 and n by n will be equal to 1. So, in that case, theta hat map will approach to theta hat mle. If sigma theta square, that is the variance of the prior PDF, is very large, in that case theta hat map will be approximately theta hat mle. Now, next is if a number of data point is large. So, as n tends to infinity, so in that case this ratio will approach 1, therefore, theta hat map will be again approaching to theta hat mle. So, as n becomes large, theta hat map will tend to theta hat mle, and as sigma theta square become large, then also theta hat map will tend to theta hat mle. Now, we will briefly introduce absolute error cost function and minimum absolute error MAE estimator. Here, C of theta minus theta hat is equal to absolute value of theta minus theta hat. This is the cost function. So, as a function of error, this is given by positive. If error is positive, this is a positive slope, and if error is negative, then this is slope is negative. So, average cost now C bar of theta hat, that is the Bayesian risk or average cost function, that is equal to E of absolute value of theta minus theta hat, that is double integration from minus infinity to infinity, minus infinity to infinity, mod of theta minus theta hat into f of theta comma x d theta dx. This is the joint PDF between theta and x. Now, writing in terms of prior and conditional PDF, we write this double integral as double integral of mod of theta minus theta hat into f of theta given x into fx d theta dx. As earlier, we can now take fx dx outside, so that we have now two integral, one outer integral and one inner integral, and this quantity is always greater than equal to 0. Therefore, the minimum can be obtained by minimizing this expression only. Thus, the Bayesian estimation problem for absolute error cost function is to minimize over theta hat integration from minus infinity to theta hat minus theta, f of theta given x d theta. This is one part, and the other part is theta hat to infinity, theta minus theta hat into f of theta given x d theta. In this interval theta hat to infinity, this theta minus theta hat will be a positive quantity into f of theta given x d theta. So, this is the integration, and other side theta minus theta hat will be negative. Therefore, we write here as theta hat minus theta into f of theta given x d theta. So, that way we have integration from minus infinity to theta hat and theta hat to infinity. Solving the estimation problem, we can show that theta hat MAE satisfy this equation, that is integration from minus infinity to theta hat MAE of f of theta given x d theta is equal to integration from theta hat MAE to infinity of f of theta given x d theta, and this is equal to half. Thus, theta hat MAE corresponds to the median of the a posteriori PDF. So, we have to find out the median of the a posteriori PDF. This is the a posteriori PDF. Its median value is the theta hat MAE. Now, we note that theta hat MMSE is the conditional mean. It is the mean of f of theta given x. Theta hat map is the mode of f of theta given x, and finally theta hat MAE is the median of f of theta given x. So, MMSE is given by the mean of the posteriori PDF, theta hat map is given by the mode of a posteriori PDF, and theta hat MAE is the median of a posteriori PDF. For symmetric PDFs, these estimators will coincide because for such PDFs mean, mode and median coincide. Let us summarize. The map estimator minimizes the hit or miss cost function and is given by theta hat map is equal to argmax theta of f of theta given x. So, a posteriori PDF we have to consider, and the mode of the a posteriori distribution will give theta hat map. Theta hat map is the mode of the a posteriori PDF. If f of theta given x is differentiable, then theta hat map is given by the map equations, that is either in terms of the PDF del theta of f theta given x at theta hat map is equal to 0, or in terms of the log likelihood function del theta of L theta given x at theta hat map is equal to 0. Applying Bayes rule, the map equations can be written in this form: del theta of log of f theta at theta hat map plus del theta of log of f x given theta at theta hat map must be equal to 0. The map estimator is related to the MLE. When f theta is sufficiently flat, log of f theta will also be flat, so that the partial derivative of the log likelihood function with respect to theta will be approximately equal to 0. So, in that case theta hat map will be equal to theta hat MLE. The minimum absolute error estimator MAE estimator minimizes the mean absolute error cost function and is given by theta hat MAE is equal to median of the posterior PDF f of theta given x. For symmetric PDFs, theta hat MMSE, theta hat map and theta hat MAE coincide. Thank you.